Hi, another trend. Let's talk about ionic radius. So overall, if we are looking at the periodic table and you are comparing different ions, you'll follow the same trend, the same rule as our atomic radius. So ions are going to increase as you go down the periodic table because you gain an energy level, and as you go from right to left, because our left-hand side is going to have the weakest effective nuclear charge. If you need a review on that, look at the atomic radius video. So for example, let's say that I'm taking a magnesium ion and I'm comparing a calcium ion. Well, the calcium is going to be one energy level larger. That means that the calcium would have a larger atomic radius than the sodium, or excuse me, than the magnesium. If I'm comparing completely different, let's say a cation and anion, let's do a rubidium +1 and compare this to a sulfur -2. So I've got my rubidium and I've got my sulfur. Looking at this, I can see sulfur is at the 3rd energy level, rubidium is at the 5th energy level. As ions, sulfur still at the 3rd energy level. Rubidium actually becomes the 4th energy level. Sulfur still has one less energy level. So I would write it like this. So you can look at the periodic table and still think shells, energy levels, and effective nuclear charge. Now, where it starts to get a little tricky is when you compare neutral atoms to ions. So let's look at a sodium compared to a sodium ion. Okay, so here's sodium. Its energy level is valence shell is going to be 3s1. I'm going to make a note of that. We are going to be at 3s1. So I'm doing the core notation, 3s1. So when it ends, its valence shell is at the 3rd energy level. Check this out. Sodium ion, okay, it loses 1 electron. So it's lost that electron. Its valence shell is now neon. Remember, that's the 2p6 right there. So by losing that electron in the 3rd energy level, its valence shell is now the 2nd energy level. By looking at the electron configuration, considering cations, it's easy to see there's an entire energy level difference. That means that the neutral of the cation is much larger. It's a whole energy level larger. And you can take this as a takeaway. The cation is always a smaller radius than its neutral element, and it's because it loses an energy level. And that's how you would explain it, that the sodium ion, its valence shell is 1 energy level lower. Okay, so that one pretty easy to see. Now let's talk about our anions. So let's compare, let's go ahead and do fluorine. Let's do a fluorine in comparison to a fluoride ion. So fluorine is going to end at a 2p5. Fluoride, this is going to gain an electron, becomes a 2p6. So here's the deal. The fluoride has gained the stability, still same energy level, but it's gained the stability of a full octet. It actually is larger. And here is the reason why, and this is something really specific that you have to memorize. The reason why the anion is larger than its neutral element is because it gains the stability of a full octet. The electrons can now repel each other a little bit more. So if I'm at my 5 valence electrons, or it's actually 7 valence electrons. We've got our 7 valence electrons. And remember, effective nuclear charge. The power of that, those protons are attracting, making that atom small. And then it gains that 6th electron in the p. So I now have a full valence shell of 1, 2, 3, 4, 5, 6, 7, 8, a full octet. We get that stability. It allows the electrons with the stability to now begin to repel each other a little bit, and the ion gets a little bit bigger. So here's your explanation. For anions, the stability, of a full octet allows the electrons to repel one another. And so the anion is larger than the neutral element. And that's something that you can take to the bank. Memorize that as well. So when you're comparing individually, you can see the cation is always smaller than its element. The anion is always bigger than its element. And the explanation here is the shell model. It's the shell model because we have one energy level difference. And over here is stability of the octet, and so the electrons can now repel one another just a little bit. Okay, here's going to be a classic question for a first year college chemistry class. So AP, here we go. We're going to take a list of atoms that are all isoelectronic with neon. So we have got the nitrogen, oxygen, fluorine, neon, and let's include sodium ion, magnesium ion, and I'm going to make these ions, -2, -3. Okay, these all have 10 electrons. They're all going to have a full octet. And you'll be asked which one has the largest ionic radius, which one has the smallest ionic radius. Well, they all end at, every single one of these is going to be a 1s2, 2s2, 2p6. So we're really splitting hairs. It comes down to effective nuclear charge. They all have 10 electrons. So whichever atom has the most protons is going to have the smallest radius because those protons have greater ability to attract the electrons. So let's look at this. If I do protons versus electrons, all of these are going to have 10. They all have 10, 10, 10, 10, 10. We have 10 electrons. The protons, so we've got our nitrogen, 7, 8, 9, 10, 11, 12. We can see that magnesium ion has the most protons. So this right here is going to be the smallest. In contrast, okay, 12 protons attracting those 10 electrons, especially those 8 valence electrons. Whereas we've got over here nitrogen, our nitride ion, there's only 7 protons attracting those 10 electrons, especially those 8 valence electrons. So this would be the largest. Largest because there's only 7 electrons. This one's, 7 protons. Magnesium is going to be the smallest because there's 12. There's 5 more positive charges attracting the same number of electrons. So if I were to put an inequality on this, the trend is going to be largest to smallest. So if you're given isoelectronic atoms, ions, look at the number of protons. Whichever one has the most protons will be the smallest because the protons have the greatest ability to attract, have a greater ability to attract those electrons. More protons, greater ability to attract. Nice discussion. Ionic radius. Have a really good day.